In this session, we'll talk about solubility as another application of equilibrium ideas. And you can find more about this in OpenStax Chemistry Chapter 15, really all the sections. Okay, so in Chem 131, you learn to classify things as soluble and not soluble. But your life experience tells you that pretty much everything is somewhere between being soluble and being insoluble. So here, we're going to think of solubility as an example of dynamic equilibrium between solids and aqueous ions. When we write solubility chemical equations, we always write them in the order of solid becomes aqueous ions. And so that's just a convention that we all agreed to. So here we have silver carbonate as a solid becomes 2 silver ions and a carbonate ion. When we write the reaction that way, the equilibrium constant gets a special letter KSP, where SP stands for solubility product. So here we see that the solubility product for silver carbonate is 8.4 times 10 to the minus 12. That's a pretty small number, which is consistent with the solubility rules that you may have learned before, that carbonates are pretty insoluble. Okay, so which of these hydroxide salts would you expect to be most soluble? The most soluble hydroxide salt is going to be the one with the largest KSP, which in this case is going to be barium hydroxide with KSP equals 5 times 10 to the minus 3. Remember that the smallest negative exponent is the largest number. So that means that this is the one that's going to go the most to the products, because remember this is written as a solid becomes aqueous ions. Which of these same hydroxide salts will dissolve the fastest? So remember that equilibrium tells us about what will happen when the concentrations stop changing. It doesn't tell us about how fast reactions happen. So we would need more information about the kinetics of this reaction if we're going to comment on which one dissolves the fastest. Okay, so let's practice writing a balanced chemical equation for KSP of magnesium hydroxide, which has a KSP of 5.6 times 10 to the minus 12. Alrighty, so like we said, the pattern is that we start with our solid, and that's in equilibrium with the aqueous ions. Okay, and so then our expression for KSP would follow the same rules that they've been following before, where we have Mg2 plus times OH minus squared. All right, you notice that I didn't include the MgOH2, the magnesium hydroxide, in the equilibrium constant expression. Why didn't I include it? Oh, because it's a solid. Remember that solids are not in our equilibrium constant expression, and that stoichiometric coefficients become exponents. Okay, so our next topic is to calculate the molar solubility. And so molar solubility is defined as the concentration that dissolves in a saturated solution at equilibrium. So we want to know how much of the MgOH2 dissolved in pure water would become ions. So it's first helpful to start out with our balanced chemical reaction. We said MgOH2 becomes Mg2 plus 2OH minus. Alrighty, So what is our initial concentration of, so in order to calculate molar solubility, we want to know what's in the solution at equilibrium. So if we want to know concentrations at equilibrium, then that's basically setting us up for a nice table. So what is the initial concentration of MgOH2 solid? Nonsense, Dr. Young. Solids aren't part of the equilibrium constant expression. What are the initial concentrations of Mg2 plus and OH minus? Well, the initial concentrations are 0 and close enough to 0. Remember, there's a little bit of OH minus from water, but we're going to neglect that. Here we see that, so we can do the change. Here the change is going to be plus x. We can't have less than 0, so we know the reaction has to move toward the products. And this will be plus 2x. And so then the equilibrium concentrations of magnesium and OH minus will be x and 2x. So we can put those back into our KSP equation, which we said before is going to be the concentration of Mg2 plus times the concentration of OH minus squared, okay, which here is x times 2x squared, or 4x cubed. And we said that 4x cubed will equal the value of KSP, which is 5.6 times 10 to the minus 12. Okay, if you solve for x, you'll find out that it is 1.1 times 10 to the minus 4. And since that x represents every unit of MgOH2 that dissolves, then x is also the molar solubility. So in other words, the molar solubility will be 1.1 times 10 to the minus 4th molar.